Swayam Prabha. Digital India. Educated India.
See, let us continue our discussion on torsion. In fact, we have done the thought experiment followed by an experiment, and we have understood certain aspects of torsion. Fine. And see, what we did was we hypothesized that I have a radial line that deforms into a curve. So, we started deliberately with a wrong hypothesis, and then we looked at the geometry of deformation, and the main point that we had a discussion was invoking the symmetry. I was able to invoke the symmetry mainly because the cross section is circular. So, about this axis geometry is symmetric. I consider the material as isotropic. So, elastic properties are identical along any direction, and the boundary conditions are also symmetric about the axis. So, based on that, we have concluded that straight lines will deform into straight lines, and we have also verified by the thought experiment when you rotate it by 180 degrees, what you have at the bottom surface when I rotate it, it is identical to the top surface. We have not only done the thought experiment, we have also seen it in the experiment. So, first understanding is the radial lines will deform into radial lines, and we also observed from the experiment that these radial lines lie on the same plane. Nothing happens to that plane. That we have not done any thought experiment, but we have done the actual experiment and seen that that plane remained horizontal. But I can also investigate that by a thought experiment. The only requirement is I should have the deformation symmetric about the axis. Anyway, you can take it, and here I can consider that this bulges out and it is symmetric about this axis. This happens on every cross section. So, this cross section also bulges out, and we know how to test symmetry. If I rotate the whole system by 180 degrees, it should come to be the same shape, which is not going to be the case, because when I rotate it, because it is bulged, I would have this as a cup. So, this violates symmetry. So, from thought experiment also you can say that these planes remain plane. It is a very important concept. It is also taken as an idealization, but when you perform an experiment, you see that very clearly in the experiments. So, it is no more thought experiment, we have captured reality in all its totality for a circular cross section, which is a slender member, and the deformations are small. All these attributes you should look at it. So, when I rotate it, you will have the same this one, that is very clear and obvious. And now I have a circular shaft that is twisted, and you see the horizontal plane as this red line, and your vertical lines are drawn blue. See, this is a cylindrical object. The line drawn at the back is magnified because this behaves like a lens. That is why you see that shade of blue thick here. And you could see very clearly that these lines remain horizontal, and then you have these two lines sheared. Fine. And in the case of a square shaft, this line does not remain horizontal, but it has a shape like this, fine. My hand was shaky, so when I drawn it with free hand, some kinks are seen. You can imagine that this is a smooth line. So this has ups and downs, and this is labeled as warping in the literature. So we don't go to the analysis of square shaft in this course. And in the case of circular shaft, one of the important understanding is plane sections remain plane before and after loading for a uniform circular shaft. It's a very, very important observation. In fact, when we graduate to bending, we would use the same idealization and choose an appropriate loading which satisfies that and develop the bending theory. Whole of strength of materials hinges on plane sections remain plane before and after loading, because using this assumption we are in a better position to appreciate what is the deformation possible. Once you have captured the deformation, you don't require to solve this by solving a boundary value problem. The deformation is understood. From the deformation, write the strain. From strain, you write the stress strain relations. So the complete solution is obtained. So the key point here is how well you have picturized the deformation clearly. So what we do in strength of materials is we choose simple loading, simple cross section that satisfy this basic idea. Plane sections remain plane before and after loading, which you can see for many problems later also. This would be satisfied. So I don't have to solve for deformation by solving the boundary value problem of the differential equations. And I have also asked you to exercise your thinking power to find out what happens in a spring, because we all start teaching deformable solids by taking the help of a spring. See, I have said we use the spring only to illustrate the force deformation relationship is linear, and the other aspect of spring is also you can easily visualize that spring stores energy. So all deformable solids will store energy. So for these two aspects we look at it, and when you look at the sketch, schematically it's easy to represent the spring like a zigzag line, and when you axially pull it, it opens up, and then when you compress it, closes up. If you want to find out what way spring resists load, it is not tension or compression. Is the idea clear? You have to look at how the spring is constructed. I have the spring which is coiled like this, and then you apply the axial pull, and in this case, it is coiled in such a manner, this forms the axis of the spring. So now what I will do is I will cut at one of the coils here. I have come like this, and then I have taken this and I have removed it, and I have drawn the diagram here, and this is the load that is applied. Can you find out what is the resistance developed at this cross section? Because it is nothing but you have a load, and then if you look at what is the way this cross section is located, this is located by the radius of the spring, you can say. What kind of force system will exist on this cross section? Because you have the load that is applied, which is along the central axis. So this will try to, it is relevant to this discussion, it is trying to twist it. You get the point? A tension spring resists the tensile load by developing torsional moment. Okay, so it is actually transmitting only torsion. In addition to this torsion, you will also have the axial force. So you will have a shear introduced on this cross section as well as a resistance due to torque applied. So if you have to design a spring, you should know what happens in the case of a torsion. It is no longer tension and compression. In a similar manner, I have also raised another question. Go and open up your cycle carrier, find out what is the load that is transmitted by the spring. Fine. So you should understand this. Make a neat sketch of this. So when you want to find out how to design a spring, you should know torsion to design a tension or compression spring. Is the idea clear? Now you need to make neat sketches. I will show the animation slowly, and you have to keep in mind that we are again analyzing only a slender shaft. I take a very small section delta z. I have blown it up for me to have clarity on what is happening in this small section. So don't get carried away by the size. It looks like a slab, huge slab, fine. So it's actually a very slender member. So I have taken arbitrary section. You can draw the lines and also label them the way that I have done it. Take your time. And what we are also going to do is, we are going to find out at an arbitrary radius r. I will also draw a arbitrary radius r, and I would like to find out what happens on this interior part of the shaft. Because we have already seen, even before developing torsion, we know that shear stress varies linearly from the center to the outer fiber. So in order to develop that relationship, it is better that we take a arbitrary radius r and find out what is the kind of dotted lines that you have to start with, and the axis of the shaft is taken as z direction, and you have the radial direction and theta direction. Because it is a circular geometry, it is better to go to a polar coordinates. And this is before twisting, fine. And this is a section somewhere in the middle of the slender shaft. Now what I do is, I apply twisting moment. When I apply the twisting moment, I have the twisted shape here. That is what we have to understand, and then find out what kind of changes that happen. And you also have the nice animation which is continuously running, which will tell you what way I have to draw the deformed lines. And first thing is, you will have to appreciate, I have a section far away from this end. So this section would have twisted by an angle phi. And I have another section which is at distance delta z away, that is the top surface. It would shift by, twist by delta phi. I have phi and delta phi is what you will have to understand. So I have this, and I have drawn the same lines here. Whatever the lines that I have drawn it earlier, I have drawn it, because my idea is, because of applying the twisting moment, how do these lines deform? Because once I understand the deformed position of these lines, we already have definition of the shear strain. Shear strain is nothing but change in the original rectangle. So we will have to investigate whether it remains as original rectangle after deformation, or is there any change. So please draw this. First you have to appreciate, I have taken a section somewhere in the middle of the section, because we do not want to study anything close to the load application point, because we all know Saint-Venant principle, fine. So we want to stay away from the end effects. So when I apply the moment, the bottom of this section would have had an angle of twist of phi, and just the slice away, that is delta z away, it will have, which we have not drawn. Now we will draw this, okay. As far as the small section is concerned, only now I am going to put the twisting moment. Because of twisting moment, this lines shifts like this, that is drawn in red, and I have this line as I have E1, F1, A1, B1 is what is the new position. D0 and D1 are identical and C0 and C1 are identical. And what you have is, I have this original line E0, A0, that is the black line, and the deformed line is the red line, because we have already seen radial lines remain radial, so the line remains straight, and this small angle is delta phi. Okay, and you can find out what is the distance E0, E1. I can find out the distance E0, E1. Can you tell me what is the distance E0, E1? R delta phi. Very good. Okay, and we will also have to investigate, and very clearly you have this. You have this sheared, these blue lines are sheared, and that is what you see here. Here it is drawn as red so that you can distinguish between the undeformed and deformed position, and also label them. We will use this drawing subsequently. You are going to see this drawing again and again in the slides. So, even if you have missed some portion of it, you can fill it up. We are going to investigate this deformation and find out which are the angles remain 90 degrees, which are the angles do not remain as 90 degrees. That contributes to the appropriate shear strain, because we have already ruled out existence of normal strains. You won't have epsilon z, epsilon r and epsilon theta, all three are 0. Among the 3 shear strains, which of the shear strains are 0 is what we will have to look at. But before that, we will first calculate the existing shear strain due to torsion, and this is again explained. Whatever I have said is again explained here. You have to appreciate that why I have shown phi here, why I have shown delta phi here. You should appreciate that, because this is taken somewhere in the middle of a slender shaft. So, I have angle of twist is phi and phi plus delta phi. And we will see that EFGH, okay, EFGH, it has gone into E1, F1, G1, H1. I have followed the same color code. I have the circles as red and then the straight lines as blue, so that you can easily visualize. You can easily visualize from this diagram what has happened. I have these blue lines sheared, which we have seen by the experiment. Same thing has happened here. Okay. So, the original right angle EHG is sheared into acute angle E1 H1 G1, which is also shown in a 2-dimensional sketch here. You have already calculated what is this. That is nothing but E0 E1. You know that is R delta phi. And you know what is this height? What is this height? Delta z. So, you have all the quantities, so you can find out what is the shear strain. Fine. And you should also be able to say, how will you label this shear strain? I have the axis R, theta, z labeled like this. Fine, think about it. We have seen that this has sheared, okay, and we are in a position to identify this angle and also this distance. This is happening between what axis? Theta and z. Okay, so I have this as gamma theta z. See, tensorially we want to have epsilon theta z. If you want to write a transformation relation, we want to write epsilon theta z. But all the development in the early part of strength of material, they have done it only with gamma. And epsilon theta z is 1/2 of gamma theta z. Okay. Now, we have to find out what is the magnitude of gamma theta z. You have already done half of it. We will fill in the mathematics and get the values. Okay. And we will also have to understand in the limit delta z tends to 0. That is what we are going to approximate. Okay. And again, this is shown for you to give appreciation that the blue lines have sheared. And we have already looked at the geometry, and you have already told me what is E0 E1. So I can have gamma theta z as limit delta z tends to 0, fine, because we write tan theta, and then since theta is small, we write the ratio, okay, the appropriate distances. So E naught E1 divided by H1 E naught will give you, and E naught E1 you already said correctly, R delta phi, and then H1 E naught is delta z. So this gives me R d phi by dz as your shear strain component gamma theta z. You will have to appreciate that this is a function of R, and how we have looked at R, this is 0 here, and you have the generic R here, and this is R max. So R changes from 0 to R max. So your shear strain also will change linearly over the cross section from the center to the outer radius. Outer radius has the maximum value of shear strain. So that is what is documented here. The shear strain varies in direct proportion to the radius, from no shear strain at the center to the greatest shear strain at the outside when R equal to R naught. R naught shows O means outside diameter, outer diameter, whichever way you can take it. And let us look at another aspect. One can also conclude, if I have a cylindrical shaft, d phi by dz is a constant along a uniform section of shaft subjected to twisting moment at the end. So I can have a twist varies linearly over the length. Okay. Now let us look at what happens in the r and theta directions. So r and theta directions means I have to worry about what is h1 d1 and h1 g1. So we have, originally it was DHG, now this is D1 H1 G1, and if you look at, if I draw the tangent to these lines, you will find that included angle is 90 degrees. There is no distortion there. If the original angle is preserved as 90 degrees after deformation, you say that component of shear strain is 0. So I have gamma r theta goes to 0. So you see these two lines, radial line and the circumferential line, and if you draw the tangents to this circumferential line and find out what is this angle will still remain as 90 degrees. Then we move on to the shear strain gamma rz. So when I have to look at r and z, I have to look at what happens to E1 H1 D1, that is E1 H1 and D1. Okay. Here again, if you draw the line, it is only sheared like this. You can see very clearly here, sheared like this here. Okay. It is only sheared like this. The blue line is shown as pink here for the purpose of this. And if you look at what is the angle between D1 H1 and H1 E1, here it will be 90 degrees. So gamma rz is also 0. So I have the strain components. 5 strain components are 0, epsilon r, epsilon theta, epsilon z, gamma r theta, gamma rz, they are all 0. The only shear strain that is existing in torsion is gamma theta z, and that is given as r d phi by dz. Is the idea clear? See, we have taken a very simple problem to illustrate. Understanding developed here can help you to solve even complex problems. I said that if you have a stepped shaft, definitely in the region of a step there will be disturbance. So you can either bring in a stress concentration factor, or bring in a factor of safety, or bring in some other empirical relation if the structure is too complex. So wriggle out of from that zone, but rest of the zone you have solution, exact solution. So that is how engineers operate. So whatever we have discussed, it is repeated as animation here. So you can ruminate and then see stage by stage how we have looked at the deformation. From the deformation, we have figured out what is the non-zero strain that is present. We have also written it in terms of the geometry of the problem. So it is obtained as gamma theta z, and then gamma r theta is 0, and then gamma r z is 0. So you have the strains given. The only restriction placed on the material is it must be isotropic. Only then I can invoke symmetry conditions. If the material is not isotropic, all my discussions go for a 6. Fortunately, many of the engineering materials can be modeled as isotropic. So whatever the relationship that we have developed can be easily applied to elastic conditions, plastic condition, linear or non-linear, okay, as far as the strains are concerned. So if the material follows Hooke's law, the stress components are given as, when you have 5 strain components are 0, 5 stress components are also 0. We have already seen in the case of isotropic material, normal stresses produce normal strain, shear stresses produce shear strain. There is no coupling. The coupling happens in other than isotropic materials. So from the knowledge that we have already gained in stress strain relation, I can find out tau z theta equal to g times gamma z theta. And you would have noticed I have used the idea of equality of cross shears or cross strains. That is what is shown here. Gamma theta z is identical to gamma z theta. Similarly, tau theta z equal to tau z theta. And now you have an expression that is g r times d phi by dz, where g is the shear modulus, you all know. So now we have the exact solution, even though we started with an hypothesis. Hypothesis is verified by experiment. So what you get the relationship now are exact solutions. And you know, I have always noticed whenever you learn the subject, because you take the shaft and then twist it here. See, initially when I hold the shaft, there may be some kind of relative motion between my hand and this member, but once I do it, I am only applying twisting. There is no relative movement of my hand, and whatever the twisting moment developed, it is transmitted by the section, and this complete surface is free. You have to appreciate that, okay. So what I have here is, you have seen how the shear strain is developed. Now we look at the shear stress. I take a small area delta A, and I have this shear component, because you know we have the symbolism. First symbol should tell the plane. This is the z plane, and the direction is theta, so tau z theta. And when I take out an element like this element is taken out and you put the reference axis. You can make a neat sketch, please. I have shear stress component developed, and you have the complementary shear. From your equality of cross shear, you know that these two shear components are equal in magnitude. And I have this labeled as tau z theta, and this is tau theta z. From your understanding of solid mechanics, cross shears are equal. So this is the shear stress that you have. That is what is summarized here. The shearing stress on the plane z and theta are of same magnitude, and each element is in equilibrium. We have not verified the equilibrium condition. We will go and verify the equilibrium condition in a short while. And you know shear stress varies linearly. We will also picturize this, okay. So I will have maximum shear stress, and then it tapers down to 0 at the center. And how do you establish equilibrium? See, whatever the shear stress developed should balance the applied torque, isn't it? So, when I write the equilibrium condition, I have repeated the same figure so that if you have missed out, you can correct your figure. I am going to write only the equilibrium condition, and the equilibrium condition should satisfy. I have also shown that this is varying as a triangular variation. On each section of the shaft, the resultant of the stress distribution must be equal to the applied twisting moment. So, your integral r tau z theta dA, this is what is shown. See, I have the shear stress acting on an area, so I can find out what is the force, and once I take the moment, the momentum is r, and I do it for the complete area. A represents the complete area of this circular cross section. That should be equal to twisting moment. And when I do this, I also get an interesting expression when I substitute the expression for tau z theta. You know, what I want to emphasize here is, suppose I take the model and apply the axial load, you can easily visualize that each cross section transmits the same axial load. Somehow when people change the problem to twisting, they have a doubt that you still have, because we have shown the shear as tangential to this on this cross section, people have a feeling that you are applying something on this surface. Okay, we have done a detailed discussion on free surface. So, what way you have to appreciate is, when I have a section like this taken out, you will have shear stresses developed on this surface that would balance the twisting moment. If I look at the lower section, this will also have the shear stress developed on this surface and balance the twisting moment, and the entire shaft will be transmitting the same twisting moment along its length. That aspect has to be appreciated clearly. Okay. So, what you have, whatever I have told you earlier, I have also summarized this in the sketch. So, all this portion what you see is a free surface. You know what is the definition of free surface. If you go and write the tensorial nature of stress developed in torsion, find out the stress vector acting on this plane, stress vector will go to 0. That is what you call it as a free surface. So, now what you have to appreciate is, when I take a slender shaft and put any arbitrary cross section, you should visualize that this cross section, what you see, develop the necessary shear stress. So, there is nothing on this surface. So, when you take a point on the surface, you should look at which plane is free surface and which plane you can have shear stress acting. That clarity has to come. Okay. Now, let me ask one another interesting question. See, I said that twisting of a square shaft is difficult from mathematical analysis point of view. When I have, instead of a circular shaft, a square shaft, you agree that all of these places is again free? From your knowledge of the solid mechanics development so far, you can find out definitely what is the stress tensor on 4 lines in a square shaft. Do you agree with me or not? I have given you the clue. I am not talking about stress. I have said stress tensor. And you have to connect it with, we have learned that this is a free surface. And you have to imagine that you have a square shaft. So, what do you have in a square shaft? You have outward coordinates. So, you know from your earlier discussion that if I have the outward corner here, which is twisted here, and it's also twisted here, what should be the stress tensor? I am happy. Okay, so the knowledge what we develop should help you to answer certain questions, if not all questions. Is the idea clear? So, even though you have a square shaft and a torsion, you may not find out the stresses completely in this course. From the knowledge you gain, you can at least say what happens in the outward corners. Excellent. Now, whatever we have discussed, a very nice simple animation is put here. I have radial lines remain radial and longitudinal lines get shifted like this, and this summarizes the complete picture of what happens in torsion beautifully. And we will just summarize the expressions. So, I have tau z theta equal to r d phi by dz, which we have seen as shear strain by looking at the deformation. From stress strain relations, we have got what is shear stress tau z theta. From equilibrium, I have got this. Now, I can substitute for tau z theta in terms of g r d phi by dz in this expression, and you get a mathematical entity. And I have also asked you a class back in mathematics, what is that it recognizes the cross section. I raise the question. I have asked you to think about it. Fine. So, when I substitute here, I get this twisting moment as integral r squared dA. What do you learn from your property of cross sections? This. Fine. So, this is also the polar moment of inertia. So, moment of inertia understands the cross section, because if I change the nature of the cross section, moment of inertia will change. So, if you say how does the mathematics recognize as your cross section, you can say that when I look at the moment of inertia, it understands the shape. If I look at area, it does not understand the shape. I can have cross sections of various geometry having the same area of cross section, but moment of inertia will change. So, it is another way of looking at it. See, while developing this, we have taken the axis as z along the shaft, and I have also said that this is Iz. But you know, when you go to bending, you may also have different axes where the Iz will have a different connotation. In order to avoid confusion, it is better that we replace in our problem solving Iz as Ip, indicating its polar moment of inertia. I may not have done that in all my expressions. So, for a circular shaft, Iz or Ip is given as Iz equal to integral r squared dA pi r naught power 4 by 2. If you write it in terms of diameter, it comes to be pi d power 4 by 32, which you will be repeatedly using it. Fine. So, you should understand that this is also the definition of Ip, because if you write in this chapter twisting moment as empty and your moment of inertia that is necessary for the calculation as Ip, you will not make a mistake when you go to bending. There should not be a confusion between the two. And we can also establish a relationship between torque and angle of twist. The rate of twist in terms of the applied twisting moment is given as, I have this expression, d phi by dz equal to mt by gip. And gip also has another name. This is also known as torsional rigidity. The product GIP is also known as torsional rigidity. Suppose I have a shaft of length L loaded at the ends by twisting moment. The total angle of twist is given by phi equal to integral 0 to L mt by gp multiplied by dz equal to mtl by gip. So, for a cylindrical shaft, you can find out the angle of twist comfortably. You know, we also have one problem which we have discussed on the variation of twisting moment along the length. We also had one portion where twisting moment was varying as a function of length. So, there you can use the integration properly. So, I can also find out in a varying twisting moment how to find out the angle of twist. All that is embedded in the expression. This expression can be used to estimate that also. But in the simplistic case, you can simply say MTL by GIP when I have a cylindrical shaft and a constant twisting moment. I said that you also have a torsional spring. The moment you say spring, you can also visualize what is a spring constant. In the case of a tension spring, you talk about axial force and axial deformation. In the case of a torsional spring, you have a corresponding, you have the force, generalized force and generalized displacement. So, instead of the axial force, you have a twisting moment. Instead of axial deformation, you have a twisting deformation, okay, angle of twist. And you have to appreciate that the angle of twist in all our mathematical development is only in radians. So, you have to convert it appropriately from radians to degrees while solving the problem, because the definitions what we have applied, all our discussion till now, phi is always expressed in radians. So, the ratio is analogous to spring constant, and so you have GIP by L can be called as torsional stiffness, and I have already said the product GIP is known as torsional rigidity. See, this idea of rigidity comes because we graduate from rigid body mechanics to deformable solids. And when you go to deformable solids, we go for small deformation. So, when you looked at the basic solid mechanics, we felt that when there is a shear, it distorts. So, that is why you call that as also modulus of rigidity. So, somewhere or the other, you want to hang on to your rigid body mechanics, fine. So, if the shaft was rigid, it would have been very, very stiff, you cannot twist it at all. So, this is also a measure of product GIP is also a measure of what is the way it can resist torsion. If the torsional rigidity is higher, you will have angle of twist will be smaller. It is higher value indicates it is more and more rigid. Okay. Now, we should also summarize this as expressions. Okay. So, you have radial lines remain straight, that is what is shown here. I have a radial line, this remains straight, and longitudinal lines remain straight, but they get spiral, they get twisted like this. And this is a famous expression. This is valid for a cross section of circular shaft of uniform cross section with only n moments applied, which is also constant. We have already derived that this angle of twist is phi by L, we have already derived, okay, that is phi equal to MTL by GIP, okay, we have already derived that. So, this is known as a torsion formula. You will have a similar expression appearing in bending, we call it as flexure formula, and these are valid for uniform cross section and only constant twisting moment is transmitted. This expression is valid. Instead of twisting moment, you will have a bending moment and appropriate moment of inertia, and also you will have appropriate normal stress. You will have an equivalent formula in bending. So, it is better to remember this formula, fine, and also understand its limitation. It is for a uniform circular cross section and constant twisting moment. And I have always told you in this course, when you look at stress component, it appears like a scalar. Do not get duped by it. While developing what are the stresses developed in torsion, we have also looked at the deformation, component wise we have looked at it, and we have evaluated the component tau theta z. It appeared only like a scalar, fine. Only when you put it in a matrix and call it as a tensor, when you do the transformation, you will recognize that it behaves like a tensor, and also you will add, when I have a combination of different loads, if I have to add them, principle of superposition, if you have to do that, you have to look at the axis. Fine. And if you are in a correct set of axes, then you will also be in a position to add them directly or transform it and then add. So, it is better that you put it in the polar coordinates in one form. I will have this as tau z theta and tau theta z like this. So, I have r, theta and z. So, you should recognize the shear stress developed in torsion is also a tensorial quantity, because we developed and reasoned out only for a component, it appeared like scalar, but it is a tensor of rank 2 and it is a pure shear stress state. You know, you will also have to recognize, suppose I take an arbitrary tau z theta and then I change these reference axes to x and y. I should recognize that I have this as tau z theta. This can be split into two components along tau zy and tau zx. Okay. So, I have this as tau zy and this as tau zx. So, when I look at the same stress state in Cartesian coordinates, it will appear little more populated. So, I have this as tau zx, tau xz. I have not shown equality of cross shear property utilized here, just to drive home the point that you have a stress tensor with populated numbers, tau zy and tau yz. See, we know a recipe whether it is a pure shear stress state by looking at the stress tensor. What is that you have to verify? We have looked at utility of stress invariants. Which invariant you have to worry about for establishing this as a shear stress state? Huh? I1. What is I1 here in polar coordinates? And what is I1 here in Cartesian coordinates? So, you have done the transformation correctly. So, you also understand that whatever the stresses developed in torsion can be represented as a tensorial notation, both in Cartesian and polar coordinates. So, in this class, we have graduated from looking at the deformation to find out what are the strain components. We found among all the strain components only gamma, theta, z exists. All other strain components are 0. From stress strain relation, we could find out tau theta z, and I said equality of cross shear says tau theta z equal to tau z theta. Then we also developed and verified whether the equilibrium is satisfied. The distribution of shear stress, when we find out what is the moment about the axis, should balance the twisting moment. And we have also learned that the entire surface is free when I twist it, okay, and then this complete surface is free. And we have also utilized this knowledge when we have a square shaft and twist it, even though we have not found out the stress distribution in the case of square shaft, you can find out on the 4 lines which form the corners. Stress tensor is 0. Thank you.